Hey y'all, I am so sorry that I am so late putting this up. If I have time, I'll explain at the end. My weekend has been nutters. Anyway, so you see in front of you the definition of the derivative, which I have tried really hard to emphasize, and I will continue to try to heavily emphasize because it's one of the easiest problems you could possibly see on the AP exam. If you look at this problem carefully, you can actually see what derivative you should be taking. This entire expression is equivalent to asking f of x equals x cubed. Therefore, that means therefore, by the way, f prime of x equals what? Right? Okay, I shouldn't say it that way. It might not be obvious to you. But if you... Oh, but I forgot the 2. Thank you, Robert, for pointing that out. I'm going to blame Robert because I don't know why. Thank you for pointing out my mistake there. I really appreciate it. Okay, so it's actually asking you for this derivative. So we look at this, and we should just be able to answer it 6x squared. So there's actually no longer any need to do the limit process and FOIL that whole sucker out. I mean, who really wants to FOIL that whole sucker out right there? Yuck. No, nobody wants to do that. So now that you know what they call in pre-cal the shortcut, which actually really isn't a shortcut, it's actually been proven. It is no longer a theorem. It is actually a definition. So your answer is to just take the derivative. So when you get to this test, which is on Wednesday, you should be able to simply take the derivative rather than use the definition of the derivative or the limit process to figure out what these derivatives are. If you look at B, you're taking the overriding function, or f of x is the cosine of 5x. So your entire derivative is negative 5 sine of 5x. And then you get down here to C, and it looks a lot different because there are numbers in it. But you still need to identify your function that you're looking at. And the function that you're looking at is f of x equals sine of x. And we're looking at the derivative at a particular point. So we're actually not looking at f prime of x, which is cosine x, but we're looking at f prime of pi over 6. And f prime of pi over 6 is not only the cosine of pi over 6, but it is 1/2. Oh, sorry. No, it's not. What was I thinking? Square root of 3 over 2. There you go. So I kind of rushed through that first bit on purpose because this is where we really need to put most of our focus. You can pause that one, rewind that one, blah, 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 that first slide. But this slide, this is going to take a lot more focus and I need to use a lot more words. And I'm trying to keep the time of this video down. So we are going to look at, I can't remember what I'm going to say. Okay, so we're going to take the derivative of the volume of a balloon in the second example, but in the first example, we're just going to review implicit differentiation. So I'm going to do the implicit differentiation on the first example without talking much and then move on to the second example, because the second example is where the meat of Friday's lesson was, and this is the part that's going to be difficult to understand. Okay, so here we took the implicit derivative of this function, or yes, it is a function, and we see that we have dx over dt. We had a question in class about why it's dx over dt and not 1, because you're not dividing the same thing by itself. Dx over dt is a rate, the rate of x with respect to t, not the rate of x with respect to x. So that's why I put this note over here. And let's see, that's all I have to say about that. But we also need to notice that we are taking that derivative at a particular point in time when x equals 4, the rate of x with respect to time is 2. So we need to plug in or substitute x with 4 and dx dt with 2 and solve for dy dt. And assuming you are a person who does not make calculation errors, which most of us do, you will get 68 there. And that is dy over dt. We've been given no units, so you don't need to worry about units. Now we're moving along to the balloon problem. And the balloon problem is more typical of the kinds of questions you're going to see. If you look carefully, the balloon is being inflated at a rate of 10 pi cubic feet per second. That particular unit right there, that is dV over dt. So it's important to note that somewhere and go through your problem slowly and mark each little piece as you go, because it's really easy to read these problems and get overwhelmed. It's better to break it down into teeny tiny pieces. So we've got this dV dt, and we've also got this formula for volume here in the parentheses. If you can hear the music I'm listening to, I apologize. I'm trying to do my laundry while I do this, and I'm waiting for the music to stop to go check on my laundry. Okay, I know you really wanted to know that. Okay, so here is our volume, and we need to think about the rate at which the radius is increasing at a particular moment in time. So we need to actually take the derivative, and we're going to need the implicit derivative. So in the next step, I'm going to do that real quick. There we go. Now our job is to replace dV dt with its value, r with its value, and solve for dr dt. We substitute in our values, and then we're going to solve for dr dt. So we get a particular answer. You might want to check with your friends and make sure I have the right number right there. I'm kind of in a rush. I'm uncertain about this final answer because I'm panicking in my head. Okay, so we've got 5/8 feet per second. And notice that I did not put my units on until the end. That's just a personal preference of mine. There we go. There's our answer. Okay, on this next one, we've got a ladder leaning against the wall, and this is where it starts getting more complex. When you see a triangle, you need to ask yourself, will I use trig or will I use the Pythagorean theorem? Every single time. In this particular case, you're going to see that the ladder is 25 feet tall. That particular value, you need to immediately decide whether that is a constant or a variable. It says nothing about it being a retractable ladder. Therefore, it is safe to assume that it is in fact a constant value. It's important that you note that right away on the drawing. Try to read tiny pieces at a time. Then it's asking you, or it's telling you, that if the foot of the ladder is being pulled away from the bottom of the wall, right there you need to decide whether or not that rate is positive or negative. So is the distance between the ladder and the wall increasing or is it decreasing? And it is, in fact, moving that way. So that is increasing. The next thing it tells you is that it's 14 feet per second. So you want to make sure that you note that right away. I'm going to call it X, even though I think we called it something different in class, because I think of my left and right values as X values. I'm going to call that 14 feet per second. Now, it asks you at what rate is the top of the ladder moving down the wall when the top of the ladder is 7 feet from the ground. So it's moving down the wall. That distance right there, or that rate, I'm sorry, I don't know why I said distance. That rate right there, the distance between the top of the ladder and the bottom and the floor, that is negative. And that is really important to think of right away. So this derivative or rate, dy dt, is negative. We also know that the ladder itself, or the y value at that point in time, not always, is 7 feet from the ground. Now, if you look at this very carefully, and you remember your geometry very well, you can see that this is in fact a Pythagorean triple. Therefore, x at this particular moment in time must be 24. It is not always 24, and that is a serious, I'm sorry, I'm being a little melodramatic and earnest. It is a really important distinction, dramatic distinction. I'm not sure what adjective to use here. Okay, so x is 24 at this particular moment in time. We know what dx dt is at this particular moment in time. We also know that we have a right triangle. We don't know anything about the angles, so it's pretty safe to assume that we're dealing with the Pythagorean theorem, so let me write that down real quick. And you can write it this way because that 25 is a constant. Now we're going to take the derivative of both sides so that we can take into account the rates. So now we've taken the derivative of both sides and we can substitute in our values. This is what is tricky about related rates, is you cannot substitute anything in until you've taken the derivative, otherwise you end up with crazy town. So we're going to substitute in our values and then we're going to solve for our missing variable. Okay, so if you look carefully, I skipped some steps right here. You should be able to figure that out on your own if you do the algebra. If you look, we got negative 48 feet per second, and we have found the rate at that particular moment in time. Again, you cannot plug in your values until you've taken the derivative because you're examining a particular moment in time. This is not true for all x and for all y. Okay, so now just to warn you, we are still on the relatively simple ones. So it's really important that you ask questions now rather than later. We've got a fish being reeled in at a rate of 2 feet per second from a bridge 16 feet above the water. Well, that was already too much information, so let's back up. A fish is reeled in at a rate of 2 feet per second. It's being reeled in, so that rate is negative. So we've got a negative rate of 2 feet per second. And that's along our hypotenuse, because the dude whose name might be Jim Bob is standing up there. Okay, that's not where he's standing. He's standing here. Oops. Oops. Somehow he's standing so that his hands are sticking out of the deck like that. Okay, so he's 16 feet above the water, and at what rate is the angle between the line and the water? The angle between the line and the water is right there, changing when there are 20 feet of line out. So that's also here. Okay, so I got all my stuff placed. I haven't figured out what we're looking for yet. We're talking about the rate, the angle between the line and the water changing. So that is what we're looking for. The line and the water, the line and the water. Boom. The line and the water when there are 20 feet of line out. Uh-oh. Okay. The line and the water. The line, at what rate is the angle between the line and the water? There we go. Sorry about that. Okay, so we know the hypotenuse and we know the side opposite the angle. So sine of theta in this instance is 16 over 20, but we need to make a general thing about it. So I'm going to choose h because that's hypotenuse. So sine of theta is 16 over h. And when we take the derivative, you have to have that general. Always have to have that general. I feel like I'm glossing over that way too much. You really need this general equation first. You can't really get anywhere without it, because you're studying a particular point in time. You're not studying that particular point in time does not describe all points in time. So we're going to go ahead and take the derivative of this, and we get cosine of theta d theta dt equals low d high minus high d low all over h squared. So we know in the problem what d theta, oh, I can't talk, what dh dt is. We know from the problem what h is, and we can figure out from the problem what theta is. So I'm going to write all that information down quickly. So at this given moment in time, the sine of theta is 16 over 20, which simplifies to 4/5, which also means that theta is arcsine of 4/5. If we know what the arcsine is, we can figure out what the cosine is. The arcsine would be 4 over 5, and that's a Pythagorean triple. That also means that cosine is 3 over 5 because it's Pythagorean triple. So the sine of theta, the cosine of theta is 3 over 5. So now we have what the cosine of theta is, so we can replace it in this equation. So we've got 3/5 d theta dt so we have 3/5 d theta dt equal to negative 16. Oh my gosh, I said the wrong thing. 3/5 d theta dt equals negative 16 dh dt, and dh dt was negative 2 all over h squared, and now we're studying one moment in time, so we can go ahead and simplify from here. I feel like I've been all over the place because I've had to interrupt to tutor my niece and to do some other things. So if this isn't making any sense, please feel free to come in and ask questions, because I feel pretty scattered and I'm feeling pretty guilty about the fact that I'm not as 100% there for you as I would like. So this is 160 over 1200. I'm going to be a lazy fraction simplifier. And I'm going to divide both by 4. And divide both by 2. There we go, 2/15. So d theta dt is 2/15 radians per second. And in calculus, you are always in radians. You are never in you're never in degrees. Okay, next slide. We only have one problem left, guys. Gals. I guess the people who missed were mostly gals. I don't know. Related rates. Water runs out of a conical tank at the constant rate of 2 cubic feet per minute. So that is your dV dt. And it's important to write that down right away. dV dt is 2 cubic feet per minute. Can't do the dot. Then I'm going to draw my little cone. And the radius at the top of the water is 5 feet deep, and the height of the tank is 10 feet. Now this has some interesting implications, and it always creates confusion later on. This means that the radius to height ratio is always going to be 5 to 10 or 1 to 2. So the radius at the top of the tank is 5 feet deep and the height of the tank is 10 feet. How fast is the water level sinking when the water is only 4 feet deep? So you can think about this many ways, but it is really important to ask yourself, how fast is the water sinking when the water is 4 feet deep? What do they really want to know? They really want to know dH/dt. And I need to pause for a second. So we look at our formula for the volume of a cone and we see that we have too many variables. We see that we want dH/dt, but we do not have dR/dt. So we cannot successfully keep it in this form and figure it all out. So we need to put R in terms of H. And R in terms of H would be 1/2 H. So we're going to go ahead and substitute in our equation the value of R with it in terms of H. And that makes for something that we can actually differentiate. And once we've differentiated it, this is 2, because that's not 2 yet. Poop, poop, poop. That's just volume. Okay, now I'm going to differentiate it, and I'm going to stop there because I've been talking forever. And right there, you have something. Once you've replaced all of the variables with all of their values, you can actually solve for dH/dt. This may not have sounded like it on your end, but it sounds like it on my end. I feel like I rushed terribly, but this took me a full 25 minutes of, I don't know, what is it called? Memory tape? I don't know what it's called anymore. In any case, I'm sorry this was so long. I hope it's not too painful. If you have questions, please, please, please come in and ask me, because this is a really difficult topic and we will be working on it quite a bit in class on Monday. We will only take one problem's worth of notes. The rest of it is going to be work time for you. Okay. Take care. Bye.